Hello there and welcome to Lower 6th Further Maths A-Level Pure Core 1 past paper, June 2014. This is new to Pure Core 1, it's volumes of revolutions through integration, so I've added this question in myself. So what we have here are two equations that form the outer shell of the ring and the inside shell of the ring. So if you can imagine, the ring sort of looks something like this on the outer shell, and something like that on the inner shell, and you put your finger in there. Right, okay, so 360 degrees around the x-axis, just as we expected. Find the dimension on the diagram in millimeters, states the maximum outer diameter of the ring. So this length from here to here is going to be the outer diameter, so that's just going to be the distance of 12 plus 12, which equals 24 millimeters. Excellent. Move on to the next part. The density of the golden ring is 19.3 grams per centimeters cubed. So we need to be careful about that unit there. That's centimeters cubed. We're in millimeters cubed, or we will be if we work out volume. So we need to divide by 1,000 and then times by this 19.3 eventually. Find the mass of the ring according to this module. So what we're going to have to do is work out the volume when this shape here is rotated 360 degrees around the x-axis. So what we're going to need to work out first are these intersection points, the boundaries for our integration. So we'll set the equations equal to each other. 12 minus x squared equals 8 minus 0.2 x squared, and we'll take the 8 over to the side, add the x squared over to this side, so 4 equals 0.8 x squared, and this is effectively 4/5, so we'll divide by 4, so we'll get x is 1/5 x squared, times through by 5, and you get x is the square root of 5, positive and negative. Great, so what we need to do now is our integration step. So it's going to be pi times the boundary from root 5 down to minus root 5 of, we're going to do the top equation first to get this area here, and then we're going to take away this area here, so we're just left with this part here. So we're going to have 12 minus x squared squared from the first bit, so we have to square our function because that's what the formula tells us to do, and the next part is to subtract 8 minus 0.2 x squared dx. Okay, so let's expand the brackets and group this together. So it's going to be 144, take away 24x squared, add x to the 4, take away all of 64. 0.2 times 6 is 1.6, so that would be take away 3.2 x squared, and then we're going to get 0.2 squared is 0.04, that would be x to the 4 dx. So what's left for us to do now is to group these bits together. So it'd be pi from the integral from root 5 down to minus root 5 of 144 take away 64, which is 80, minus 24x squared, double negative, so it'd be add 3.2 x squared. So that's going to be minus 20.8 x squared, and 0.4, sorry, x to the power 4, take away 0.04x to the power 4, So that'll be plus 0.96 x to the 4. Great, so now we need to do that bit of integrating. So it's going to be 80x take away 20.8, and we increase the power by 3, so then we have to divide by 3, and then plus 0.96 over, and it would be x to the 5 now, so we divide 3 by the 5, and we're going to evaluate this between root 5 and minus root 5. Excellent. So what we get here is, let's get our calculator out. So we'll plug that into the integral symbol. So you select the button that's just underneath the menu button at the top. Integral, you use your direction buttons to navigate to the root 5 and the minus root 5. Type in your function you want to integrate, and you get 224.203 times pi. So we'll times that answer by pi. We get 704.35 millimeters cubed. Now, given that we want this answer in centimeters cubed, what we're going to have to do now is do 704.35, divide that by 1,000 to get it into centimeters cubed, and for every centimeter cubed, the weight is going to be 19.3 grams. So what we'll do is we'll times by 19.3 and divide by 1,000, and that will get us our mass. So on your calculator, times that by 19.3 divided by 1,000, and you get 13.59, or in other words 13.6 grams per centimeters cubed. Perfect. So for part C, give one reason why the actual mass of the ring is likely to be different from the answer in part B. Well, you can have any reasons, such as the gold may be void of impurities or have impurities on it, so it may not be quite real gold, it may have some other chemicals mixed in there, or the actual dimension of the ring and the shape of the ring may vary ever so slightly differently from these equations that are given here. Any reason like that you can use. You can't use the any reasons such as I've rounded earlier up in my calculations here, so I may have not been as accurate. That's your own fault. You need to mention some reasons to how the model is set up, not with how bad your calculations are. 12 marks for that in total.